In this video, you'll learn everything there is to know about earthquake loads. So even if you're a complete beginner who has no idea as to what an earthquake is, by the end of this video, I'm pretty confident that you will be able to do a complete static analysis all by yourself. In this video, we'll be covering primarily the static analysis method. We'll be taking you through a problem statement. I initially thought of doing this simply in theoretical concepts. However, with popular community demand and feedback, here is a problem statement that we will be solving in this video. So I'll be taking you through what is called a design-based shear calculation. Now don't worry about any of the terms here. I'll be taking you through all the terms. We'll be talking about the AH, which is the design horizontal acceleration coefficient, quite a mouthful. And we'll be calculating the seismic weight of the building. Using all this, we'll be calculating lateral forces at different levels of our building. So this is going to be an exciting video, a lengthy video, but an exciting video nonetheless. And if you have ever had any confusions with respect to earthquake loads, this video will solve it for you. And I'm very, very, very confident of that. So without further ado, let's jump into the actual video. If you're new to this channel, do consider joining our private Facebook group. It has over 4,000 members already. Also, do check out the channel for more videos. And while you're there, do not forget to subscribe and hit that notification bell. Finally, I have a second channel called the Binary IQ, where I share different kind of technical stuff like web design, video editing, graphic design, and many other digital tips and tricks. So do support that channel as well. Subscribe and hit the notification bell out there as well. All the links, that is the link to the Facebook group and the link to this secondary channel, will be down in the description. After you're done watching this video, do check those out. So with that said, let's get going. Now this is what an earthquake looks like, shaking buildings. And in order to understand the complexity of this shake, let me take you through a brief onboarding process of what we'll be going to do. In general, there are different kinds of seismic waves. Some are called body waves, some are called surface wave. All in all, what they tend to do is make the ground shake and make the buildings fall. Well, not exactly. That is not what they are for, but that is what they end up doing. Now, these waves combined, that is the body waves and the surface waves, create a ripple in the ground, which ultimately results in additional forces on the building. And in our design of earthquake loads or earthquake resistant buildings rather, we are trying to find what kind of forces are included or generated due to these loads. So let's simplify this whole thing. Now these different waves will end up resulting in different kinds of ground movement. These could be very complex to very simple. Since we are not here for the complex, we are trying to simplify things. So let's simplify this entire city first. So let's deal with just a building for now. And this complex movement, which is shown on the left, can be simplified further by understanding a simple concept of the orthogonal axis. Yes, it is a bit too simple, and that is what makes it beautiful. All the ground movement or all the forces that are generated due to an earthquake can be simply broken down into three vectors. There will be some kind of force which will be generated in the x direction. There will be some kind of force which will be generated in the y direction, and some kind of force will be generated in z direction. That will result in the movement of this building or the ground itself in the x-axis, in the y-axis, or in the z-axis. And the combination of these three results in varying complexity of ground movements. Having this basic idea that every force will be broken down into x, y, and z axis or along these axes makes our calculation very simple. Let's simplify it even further. When it comes to earthquakes, the horizontal forces due to earthquakes are the predominant forces. That is, the forces in the x direction and the forces in the z direction. So everything that we had to do with the y-axis is already gone, and what we are left with is forces in just the x and the z axis. That is all what we need to find out when it comes to earthquake loads. So let's do that exactly. In this video, we will be utilizing the IS code 1893 part 1, which has been recently revised, not recently, but a few years back in 2016. This is the code for the criteria of earthquake resistant design of structures, and we'll be utilizing the concepts and standardizations provided in this code. Now, as per this code, there are two methods of evaluating the earthquake loads. One is the static analysis method and the second is the dynamic analysis method. In this video, we'll be utilizing the static analysis method. We'll be going very deep into the static analysis method, and by the end of this, you will know everything there is to know about static analysis method. By the way, if you do not have the IS 1893 with you and you're finding it hard to download it on the internet, I will be sharing a link to that code in the video description. You can check that out along with the other links of the Facebook group as well as my second channel. So let's move on with this static analysis method. In learning about the static analysis method, we will be going through a problem statement. Now, this was by popular demand. The community wanted a problem statement to accompany the actual learning process, and that is what I have done here. So this will make your learning very easy, and I'll walk you through the entire thing. So on the left, we have the elevation with different floor heights. So we have a 4200 mm. So all these values are in mm. So we have a 4.2 meter height. We have a 3.2. We have a 3.2 and a 3.2. On the right side, we can see the plan with 4 spans of 5 meter each and 3 spans of 5 meter each. So this is going to be a building which we'll be designing. Now the specification of the buildings are as follows. We have a building type. So we'll be designing an office building which is situated in Shillong, which is the capital of Meghalaya, which is a state in India. The soil on which the building is to be constructed is medium stiff, and the structure type is going to be a reinforced concrete frame structure, which is in short called the RC frame structure. These are the dead loads. So there will be dead loads on the floors. So on these 3 floors, the dead loads are different, and on the roof, it is a bit different. Similarly, the live loads on the floor, which you can see is 4 kilonewton per meter square, and on the roof, it is 1.5 kilonewton per meter square. But before we jump into the actual analysis, we have to understand the basic concept as to what we are trying to calculate. What are we trying to do in the static analysis method? Are we trying to calculate vibrations? Are we trying to calculate displacements? What are we trying to calculate? Now, the answer is actually very simple, and you must have guessed it too. We are trying to calculate some kind of earthquake or seismic load. Now, what is load? Load is basically some kind of force. And if you remember a few slides back, I talked about the concept that when it comes to earthquake, only horizontal forces are the predominant forces. So all in all, we are trying to calculate what is called a horizontal force, or in the engineering terms called lateral force. So this is what we will be trying to calculate. So a lateral force would be a force in the X or the Z direction. So this is going to be a horizontal force. So now we have some understanding as to what we are trying to calculate. Let's go on to actually calculating it. Now, static analysis method, as per the IS 1893, gives this formula for calculation of what is called the design base shear, which is nothing but the lateral force which we're talking about. So we are trying to calculate this VB, which is made of this AH, which is a strange term, and you can see it's called the design horizontal acceleration coefficient. So a lot many things going on there. W is the seismic weight of the building. So this is some kind of a different weight too. Don't worry, we'll be breaking this down step by step. So let's break down the W first. So W is the seismic weight of the building. This is the weight of the building at the time of earthquake. Now you would be thinking, how would one know how much weight is available on the building during an earthquake? First and foremost, all the dead load of the building will be there, even when there is an earthquake and even when there is not an earthquake. When it comes to live load, we make an educated guess on the basis of probability as to how much weight would be available at that time. So say we have a live load of 4 kilonewton per meter square. We assume that during the earthquake, it is a very small possibility that the entire live load will be present. That is, the building would be occupied to its brim. And in that case, we slightly reduce the live loads. All in all, it will be a combination of the dead load plus the live load. And we'll be talking about that in a bit. Finally, W is going to be the load. This is the gravity load. So all this load will be acting downwards. That is a very simple way to understand it. And hence it is a vector. Next is the AH. So AH we saw a bit earlier. AH was the coefficient, some kind of coefficient. What a coefficient is, it's a scalar value. And this AH will lie between 0 to 100. So a minimum value of AH would be 0. The maximum value would be 100. And in general, it will lie somewhere between 0 and this 100. So we have our two parts to the equation. So we have an AH, which is a coefficient from 0 to 1. And on the other side, we have the weight of the building during the time of the earthquake itself. If we multiply these two, we get the lateral force or the horizontal force, which is called VB. So ultimately what we are trying to do is find out that coefficient. We are trying to find out the total weight. And if we multiply both of these, we get a horizontal force called the base shear or the lateral force. So let's go ahead and calculate all these three things. So we'll start off with the AH, which is called the design horizontal acceleration coefficient, which I'll call coefficient from now on so that it's much easier for you to understand. But before we go ahead doing that, we have to understand that we will try to minimize AH because weight of the building will most likely not be in your control. What we have in control is the AH, as we'll see in a few minutes. So what we should be trying to do is minimize this value of AH. The more we minimize it, the lesser the value of the VB would be. And that would help create an economical building. With that said, let's decode this AH value. So as per the IS 1893, this is the formula of AH. Quite a daunting formula if you see it for the first time, but it is going to be so simple by the end of this video that you would be surprised. So let's look at it from a layman's perspective first, and then we'll go into the technicalities. So we have a few terms going around here. The first term is Z, which is kind of everything you need to know about earthquake. So if there is a greater earthquake, of course, the value of AH should be higher. Now in this case, it's not actually the earthquake, but the probability of the intensity of an earthquake. So if you are in a zone or an area where earthquakes are more prominent, this value should be greater, which will ultimately make the value of AH greater, which will ultimately make the value of VB greater. So the first term is talking about the earthquake itself. The second term, which is SA by G, is talking about the site condition or the soil conditions. Depending upon the soil, the values will differ. After that, the value of R, which in a way depicts the building strength. So as you can see, AH is inversely proportional to R. That is, if R increases or the building strength increases, the AH value as per common sense and logic should go down. So the stronger building you have, the lesser would be the force generated due to earthquake. And that is what it exactly is. Finally, the last puzzle to this equation is the I, which is the importance of the building. Now, this is going to be directly proportional to AH. If we are going to design an important building like a hospital, we'll be trying to make it resist more of the earthquake, which again is common sense because you would want your hospital to be standing even when an earthquake, which is much greater than your expectation, comes. You want the hospital to be standing right there. So greater the importance of the building, greater would be the AH, and greater would be your design forces. So this is a layman's version of this entire equation. Now let's see it from a technical point of view. So the first part of it is the Z, which is called the seismic zone factor. Now, as per IS 1893, the entire country of India has been divided into 4 parts or 4 zones rather. Zone 2, Zone 3, Zone 4 and Zone 5. And Z values with respect to each are given below. So for Zone 2, it is 0.1. For Zone 3, it is 0.16. For Zone 4, 0.24. And for Zone 5, it is 0.36. Earlier, there used to be 5 zones, of which the Zone 1 has now been discarded and everything starts from Zone 2. In order to find where you are located or in which zone you lie, you can simply use the IS 1893 map, which breaks down the country into different zones. So as you can see, the blue portion of the map defines the Zone 2. The yellow portion defines the Zone 3. The green defines the Zone 4 and the orange defines the Zone 5. So the complete northeast portion of India is the Zone 5, and you can locate your city using this map. However, IS code also gives you a list of cities defining their exact zone and the Z values. So let's find out the Z value of our question. Now, if you don't remember our problem statement, this is our problem statement. And in our case, the location of the building was in Shillong, which is in Meghalaya, which is in the northeast. So as per the previous map, we can easily locate that our northeast is completely in Zone 5. However, we could also use the list of cities which are given in the IS 1893 itself, and we can locate where Shillong is. So as you can see, Shillong is Zone 5 with a Z value of 0.36. So we have our first part of the puzzle. We have our Z as 0.36. Let's move on to the second part of the equation, which is everything to do about the soil or the site condition. Now this in technical terms is called the design acceleration coefficient for different soil types. Let me first show you a graph which depicts the value of SA by G. Now this is for the static method as per IS 1893, and this has 2 parts to it. The first part is the time period, which is T, and the second part is the soil itself. So depending upon the natural period of the building and the soil type, we will be getting the SA by G values. However, just keep in mind that the maximum SA by G value is 2.5. Now, of course, we won't be using this graph to evaluate SA by G because IS 1893 has quite conveniently given us some formulas to work with. We will be using the equivalent static method because we are working with the static analysis right now. And as per static analysis, this is the value of SA by G. Now, again, this looks a bit confusing, but we will be breaking this down in a minute. So let's first figure out which soil are we dealing with. If you don't remember the question again, this is the problem statement for you, and the soil which we're trying to deal with is the medium stiff soil. So let's locate our medium stiff soil sites, and this is where we lie. So we have our SA by G values figured out. However, we exactly don't know what values to adopt because there is one more angle to this equation, which is the time period. So let's calculate this value of T. Now, the value of T will depend upon the different kinds of building and the height of the building in general. So for a bare moment resisting frame buildings without any masonry infills, these are the different equations. This is not the case which we are dealing with. The second, that is the buildings with RC structural walls. This is the strange formula which we should do. But again, this is not going to be our building. Our building is a simple building which will fall into the criteria of all other buildings. So we will be working with this formula. Now this formula of T again has two variables to it. One is the H, which is the height of the building, and one is the D, which is the base dimension of the building. Let's break that down one by one. Let's talk about the first part of the equation, which is the H. H is the height of the building. Now if you remember our elevation plan, this is the elevation plan of our building. And as you can easily see, the height of the building in this case would be 4.2 plus 3.2 plus 3.2 plus 3.2. Everything is in meter and the elevation shows it in mm. The value of H comes out to be 13.8. So we have done our first part. Now the second part, which is the base dimension of the building, is a bit tricky here because if you'll see the plan, the base dimension is twofold. Assuming this to be our X direction and this to be our Z direction, you can see the values differ. So that is what we'll be trying to find out. So as per our plan, there are going to be two directions. The first is the X direction and the second is the Z direction. As per the X direction, we have four spans of 5 meters each. Hence, we get a value of 20 meters. So the base dimension is 20 meters along the X axis and the base dimension is 3 spans of 5 meters each. That is 15 meters along the Z direction. So we have our dx and dz values, and of course depending upon this dx and dz values we'll get different values of t. So one will be t along the x direction, which will utilize the value of 20, and the other will be tz, which will be utilizing the value of dz, that is 15. Hence we get the values of tx and tz as 0.28 and 0.32 seconds. Let's go back to our SA by G formula, and if you try to locate, you can simply find the value of tx and tz lying in this zone. So we have a value of 2.5 on our hands. So SA by G in the x direction as well as SA by G in the z direction both comes out to be 2.5. This is the value which we will be having. So let's note that down and move on to the next part of the puzzle, which is the response reduction factor, or in layman's language, the building strength. As per IS 1893 again, we have different kinds of criteria which give different kinds of R values. Right now we are dealing with moment resisting frames. So that is what I have shown you on the screen here. Now these moment frames are of different types. These could be ordinary moment resisting frames or OMRFs. These could be special moment resisting frames, or these could be steel. However, we don't know which kind of RC frame our building is. So we have two options here. One is the ordinary one and one is the special moment resisting frame. Which one is our building? We just know that our building is going to be an RC frame structure. The key to this puzzle is finding a small note on the IS 1893, which conveniently says that RC, that is reinforced concrete and steel structures in the seismic zone 3, 4 and 5 shall be designed to be ductile. Now ductile detailing comes as special moment resisting frames. So all in all, we are dealing with a special moment resisting frames giving us a response reduction value of 5 because we were lying in the zone 5. So we have our third part of the equation. Let's move on to the final part of the equation, which is the importance factor. Importance factor, as per IS 1983, divides the structure types into three categories. One is the important buildings, one is not so important, and the last one is normal buildings. So important buildings would be school buildings, hospitals, railway stations, airports, malls, and so on, where there is going to be either a lot of gathering or which is required as an emergency building during an earthquake or during any calamity. So an important building is given a value of 1.5. As you can understand, I is directly proportional to AH as opposed to response reduction. So greater the response reduction, the lesser would have been the AH. However, in case of importance factor, if you're designing a hospital building, it has to be designed to resist a greater force. And that is why the importance factor for important buildings is 1.5, which is 50% more than for all other buildings, which is just a value of 1. However, we are not bound by these values as per the note given in IS 1893, that the owners and the design engineers can choose the value of importance factor more than those mentioned above. So you can actually use a value greater than that depending upon the economy and the strategy of your building design. Now, as per our problem, the building type is going to be an office building, which in this case falls into the third criteria, that is all other buildings. So we get an importance factor of just 1. So just like that, we have our 4 parts to this equation calculated. Let's find the value of AH. So doing a simple calculation with Z being 0.36, SA by G being 2.5, R being 5 and I being 1, we get a value for AH to be 0.09, which is equal to 9%. So if you remember the simple diagram which I showed you earlier, AH is the coefficient, which is right now 9%. So whatever the seismic weight of the building, 9% of it would be the value of VB. And it is as simple as that. Now let's evaluate a few different criteria just to understand this AH even further. Say we were in zone 2 instead of zone 5, we would have had a value of 2.5%. So AH would have been drastically reduced. And it is common sense because in zone 2, the earthquakes are going to be less severe and hence the design should be less severe too. If you were designing an ordinary RC building, the AH would have increased because an ordinary RC building would not be immune to an earthquake as much as special moment resisting frame we just created. So instead of having a value of 9%, we would have had a value of 15%. And if we consider an important building, that instead of designing this office building, we would have designed this building as a hospital building, for example, we would have had a 50% increase in the value of AH. That is a 50% increase in the value of VB ultimately. So let's break down the maximum and the minimum cases. That is the maximum plausible cases and the minimum possible cases as per the IS 1893. So the minimum value of Z is going to be 0.1 for the zone 2 and the maximum value is going to be 0.36 as per zone 5. The SA by G values, if you would see the graph or the equations, is going to be 0.25 and the maximum value of SA by G is 2.5. Since R is inversely proportional, we'll be utilizing the maximum value for calculating the minimum value of AH because again, it is inversely proportional. So the maximum value of R is 5, which will result in the minimum value of H, and the maximum value of AH would be gained by getting the minimum value of R, which is 1.5. The minimum value of importance factor is going to be 1 and the maximum which you just saw is 1.5. Getting these two values, we are able to find out the minimum values and the maximum values of AH. So this is going to be the minimum value of AH, which is 0.25% of the VB, which is almost negligible, and a maximum value of approximately 50% of or half of the seismic load. So all in all, your AH will lie between 0.25 and 45. In our case, as you can see, the problem case, the value came out to be 9%. So I hope that makes everything about AH very clear. So we have one part of VB done, which was AH. So we have 9% of the equation. Let's go ahead and find this other parameter, which is called W. So W is the seismic weight of the building. As per IS 1893, seismic weight of each floor would consist of full dead load plus an appropriate amount of imposed load. So dead load is going to be universally there even if the earthquake comes or not. However, imposed load is a probability variable. Depending upon the different kinds of building, there will be an appropriate probability as to how much amount of imposed load should be taken. And we will look at that value in a few minutes. All in all, we must understand that the seismic weight of the building will consist of the seismic weight due to dead loads and the seismic weight due to live loads. So we'll be working with dead loads and live loads both. In our problem statement, we had the dead loads given different for all the floors. So these 3 floors had a different load value, both dead load and live load, which was 12, and the roof had a different value of 10. Similarly, in case of live loads, we had a different value for floors and a different value for the roof. So we will be calculating the seismic load at different levels first. So this is going to be our W1. So this is our W1. This is going to be our W2. This is going to be the W3, and this is going to be the W4. So we'll be working with these 4 levels. And it's quite understandable that the value at W1, W2 and W3 will be the same, because for all floors, the values have been given the same. However, for roof, it will be different, because for roof, both the dead load as well as the live loads are different. So all we have to do is calculate 2 values, one for all the 4 floors and one for the roof. In order to calculate those weight values, we have to first calculate the area of the building. So each floor is exactly the same, and the floor area as per the plan can be calculated very easily. So we have a length of 4 spans of 5 meters each, which is 20 meters. And we have a width of 3 spans of 5 meters each, which is 15 meters. So the area would be 20 meters into 15, that is 300 meters square. So let's calculate the seismic weight due to dead loads on each floors first. So the area of each floor, which we just calculated, is 300 meters square. The dead load on all the floors, as per our problem statement, is 12 kilonewton per meter square. We read earlier that the complete or full dead load is to be taken. That is, the component of dead load is going to be 100%. So the total seismic weight on each floor due to the dead load will be the value 12 multiplied by the area 300, which comes out to be 3600. So this is the dead load, and this is the dead load on each floor. So let's find out the live load now on each floor. The live load values, however, will not be 100% applied. As per the table 10 of IS 1893, it clearly states that values of live load up to and including 3 kilonewton per meter square will have a contribution of only 25%. And everything above 3 kilonewton per meter square will have a contribution of 50%. So that is what we are working with. And in our case, the value, if you remember, is 4 kilonewton per meter square. So we will be working with this contribution of 50%. So let's do that. The area remains the same, that is 300 meters square. The live load on the floors was given as 4. The component of the live load as per the previous slide is 50%. So we can simply calculate the value as 4 into the area, that is 300, into the 50%, which comes out to be 600 kilonewton. So the live load on each floor is 600 kilonewton. With the dead load and live load in our hands, we can easily calculate the total seismic weight on all floors. So the dead load is 3600 kilonewton, the live load is 600 kilonewton. Since W1 is equal to W2, which is equal to W3, we can easily calculate the values by simply adding 3600 and 600. So we get the value of 4200, which is equal on all the floors. Now let's talk about the roof. So we have one part of the equation. We have the weight on each floor done. Let's move ahead to the weight on the roof itself. For the dead load, we'll do the same thing as we did. We have the area, which is common, which is equal to 300. The dead load on the roof was given as 10 kilonewton per meter square. And the component of dead load again remains the same, because dead load is not going anywhere. Total dead load comes out to be simply 10 into 300, which is 3000 kilonewton. When we're trying to find the live loads on the roof, however, IS 1893 very strictly states that the imposed load on roof need not be considered. So all in all, the contribution of live loads on the roof becomes 0. So when we are trying to calculate it, the component of live load becomes 0. And the live load comes out to be 0 itself. Let's calculate the total seismic weight on the roof. We found that the total dead load was 3000, and we found that the live load contribution on roof is 0. So all in all, we get the value of 3000 kilonewton for the seismic weight on the roof. Let's combine all these. So we have the value of W1, W2 and W3, which were equal to 4200 kilonewton. And we just calculated the value on the roof, which is 3000 kilonewton. All in all, the total seismic weight of the building comes out to be 15,600 kilonewtons. And using this simple equation, we now know the value of W as well as AH. So we found the AH to be 9% and we have just found the W to be 15,600 kilonewton. And using this, it is now too easy to calculate VB. So we'll multiply 9% by the total seismic weight, which is 15,600, which comes out to be 1404 kilonewton. So we now know the value of VB, which is 1404 kilonewton. This is the total design base shear, and in common language, this is the total lateral force which we wanted. So this is the force which will be acting in a horizontal direction on this building. Now, if you remember earlier that the values in the X and the Z direction came same because the value of SA by G was same. So all in all, VB in the X direction as well as VB in the Z direction is going to be exactly the same. That is 1404 kilonewtons. So this is the force which is acting on the building. However, we still don't know as to on which point is this load acting. But we know that this load is the total horizontal load which is going to be acting on the building. So the next part of the equation is finding out the values or the distribution of this load on various floors. And conveniently enough, we have a method for that in IS 1893, which gives the exact formula for calculating the lateral forces at different levels. Now, this formula seems very, very daunting. But don't worry, it's as easy as it has been till now. So we will break down this formula. So let's first remove as to what QI, WI, HI looks like, and I'll explain it on the way. In simplest of the languages, just remember it to be something like this. So we have a QI, which is the lateral force, that is a horizontal force, but which is made up of KI and VB. So the equation in the bracket, I have converted it into KI so that it's much easier. And the VB is the horizontal force or the lateral force, which we just calculated. So just like earlier, the KI is some sort of a coefficient, which will be a value between 0 and 1 or 0 and 100%. And VB is the value which we just calculated. If we multiply these two values, we'll be getting the forces at different levels. So all we are trying to do is find the value of KI at different levels. And we will do exactly that. So let's start off. These are the story levels. So we have our first story, second story, third story, and the fourth, which is the roof. We just calculated the weight or the seismic weight of the building, which is the WI. So we calculated the value of WI as 4200, 4200 and 4200 on the first, second and third floors. And on the fourth floor, we had a value of 3000 kilonewton. HI is going to be the height of that floor. So the first floor is at a height of 4.2. The second floor would be at a height of 4.2 plus the next, which is 3.2. And it keeps adding on. So these are the floor heights from the base. So we have our value of WI, we have our value of HI. Next, we need to find the value of WI into HI squared. So we simply multiply this value of 3000 by the square of 13.8 and we get this value. And similarly, we'll get all these values. Next part of the equation is actually finding that KI. So we are interested in this KI. We have our WI into HI square. And this value is actually this value. So it's summation of the WI HI square. In order to find the KI values for the fourth floor, for example, we'll be simply dividing this by the value of this. So we get a value of 4.424. And similarly, we'll be doing it for the different levels. We'll be dividing this by the value of summation of WIHI square and so on. So we get all these values of KI. Next, all we need to do is multiply this coefficient by the base shear or the lateral force to get the values. Now, as I said, we have two directions on which this load is going to be acting. However, in both the directions, the values are going to be exactly the same because our AH was exactly the same on both the directions. So simply multiplying 0.424 by 1404, which was our VB, we get the value of 595, and simply multiplying 0.35 into 1404, we get the value of 491 and so on. All in all, we have divided this VB into these subparts on different levels. So let's see it from a little bit of a different lens. We had the value of KI at different levels and we have the value of VB, which is 1404. Simply multiplying these two, we get the lateral forces at different levels. So this equation can simply be turned into this, where the KI values are 42%, 35%, 17%, and 6%. So 42% of the entire VB is going to be this value, 35% of the entire VB is going to be this, 17% of the entire VB is going to be this, and 6% of the entire VB is going to be this value. So we have all these values done, and let's simplify it even further by looking at what is actually going on. So we have a complete value or a total lateral force value of 1404, which is acting on the building. Now this 1404 has been divided at different levels. So on the first floor, the contribution of this VB is going to be simply 77 kilonewton. So out of 1404, we have a contribution of 77 kilonewton acting at a level of the first floor. This contribution increases as the levels go up. So at the second floor, it is 17%, that is 240 kilonewton. So 240 kilonewton out of 1404 kilonewton is acting on the second floor. On the third floor, it is a 35%, and on the fourth floor, it is a 42%. So as you see, even though the load on the fourth floor or the roof was way less, the actual values of shear as the height increases, and that is very much common sense. The higher the building, the greater will be the shear felt at the top. So I hope it made sense. Let's summarize it quickly. So we dealt with the static analysis method, wherein we tried to find the total lateral force, which was VB, and VB had two parts to it, AH, which consisted of different variables, that is Z, SA, G, R, and I. We broke down the zone, the SA by G, the soil values, the R response factor, and the importance factor. Finding this, we got the AH values as 9%. We went ahead and calculated the total seismic weight of the building, considering the dead load and the live loads, and we got the values at different levels. Using this, we got the value of 9% for the AH and a load or a total seismic load of 15,600 kilonewton. Ultimately, we got the value of VB as 1404 kilonewton, which we ended up dividing into different floor levels by using this complicated and yet simple formula, which we found out to be shared unequally among the floors. The lower floors take up a lot less shear, and as you go high, the shear values increase. So I hope this video made sense. I have not gone through the stat analysis just as now because I did not want to make this video longer than it needs to be. That video is coming up next. If you like this video, do not forget to hit that like button. And if you're not already subscribed, do hit that subscribe button and the notification bell. Also, before going away, do check out my other channel and support me out there too. The links to everything that I've talked about will be in the description. So you'll find the link to the Facebook group. You'll find the link to my other channel, as well as the link to IS 1893 part 1. So do check out the description, find whatever you need. Thank you for watching, and I'll see you on the next video.